In this video, we're going to work example problems related to precipitation reactions. Precipitation reactions in aqueous solution. So let's get started. Two aqueous solutions of silver nitrate and sodium chloride are mixed. Which of the following diagrams best represents the mixture? Okay, so we're starting off with two separate solutions. One is an aqueous solution of silver nitrate, and the other is an aqueous solution of sodium chloride. And so since it says that these are aqueous solutions, that is telling us that these compounds are dissolved in the water. They're soluble in water, because otherwise you wouldn't refer to their states as aqueous, right? You would just leave it as whatever its standard state is at whatever the conditions are of temperature and pressure, most likely standard temperature and pressure, solid, liquid, or gas. Okay, so we know that these compounds are dissolved in water, but we also know that these are ionic compounds. In fact, for all of the precipitation reactions that we're studying in this chapter, all of these reactions are going to involve strictly ionic compounds. Okay, which means that since these are ionic compounds, we know that they're strong electrolytes as well. So they're going to break up into ions completely in a non-reversible reaction in aqueous solution in water. So what that means is you've got an aqueous solution of silver Ag plus cations and NO3 minus anions floating around everywhere, and then a separate aqueous solution of Na plus cations and Cl minus anions floating around everywhere, dissolved in water, hydrated in water. And now you mix these two solutions. So right after you mix the solutions, initially what you get is something like this. Okay, but now after some time has elapsed, does the solution stay, the resulting mixed solution stay like this? Or does an ionic compound precipitate out? Well, to check that, we need to mix and match the cations and anions. So when the silver plus cations interact with the Cl minus anions, is the result an ionic compound that's insoluble in water? Well, we need to check the solubility rules for common ionic compounds, because again, with these precipitation reactions that we're studying in this chapter, they're strictly involving ionic compounds, and we're thinking about in water at just room temperature. Okay, so we can see that all halides are soluble, with one of the exceptions, though, being if this halide involves a silver cation. Okay, so in that case, what that tells us is that the silver chloride is going to precipitate out of the solution. All right, but what about the sodium nitrate? Maybe that precipitates out as well. Well, okay, all compounds containing the sodium cation are soluble, and there's no exceptions. So therefore, the sodiums and the nitrates are going to stay dissolved, the blue and the green, okay? And then the gray and the orange are going to precipitate out, going to form an ionic compound and precipitate out. So this is the diagram that represents the resulting mixture. Okay, two aqueous solutions of potassium hydroxide and magnesium chloride are mixed. Which of the following diagrams best represents the mixture? Okay, so these are two aqueous solutions. So we know that these two ionic compounds are soluble in water. Again, because it's telling us that they're aqueous solutions. You can't be aqueous unless you're dissolved in water. Okay, now once these two solutions are mixed, you're going to get something like this, where everything's just, all the ions are floating around. But once they get to be able to intermix, does it potentially just stay like this, or do you have precipitates that come out of the solution? So what happens when the potassium cations interact with the chloride anions? Okay, well, all compounds, ionic compounds containing potassium cations are soluble with no exceptions, okay? What about when magnesium interacts with the hydroxide? Okay, so all hydroxides are insoluble, but do we have any exceptions here? So alkali metal ions and the Ba2 plus ion. Well, magnesium is an alkaline earth metal. So, okay, magnesium hydroxide is insoluble. So the green and the red precipitate out, and the purple and orange stay dissolved. Characterize the following compounds as soluble or insoluble in water. Okay, so they're giving us some ionic compounds here. All right, so we're starting off with calcium phosphate. Let's just go to the solubility rules for common ionic compounds. And they're implying here that we're talking about, in water, but at room temperature. Okay, so phosphates are all insoluble with exceptions of alkali metal ions, the compounds involving alkali metal ions, and the ammonium ion. So calcium should be an alkaline earth metal, right? Yes. So this is insoluble. What about manganese hydroxide? Hydroxides are insoluble with the exceptions of compounds containing alkali metal ions and the Ba2+. So manganese is just a transition metal, so insoluble. All right, silver chlorate. So chlorates are all soluble with no exceptions, so soluble. Okay, potassium sulfide. All compounds containing potassium cations are soluble. No exceptions. Okay, write ionic and net ionic equations for the following reactions. So we're starting off with, we're mixing these two aqueous solutions, that have ionic compounds dissolved. Okay, and so the molecular equation, we can start with the molecular equation. In the molecular equation, we just leave all the compounds with their full chemical formulas, even if they do dissociate into ions in solution. So we say, okay, silver nitrate plus sodium sulfate, aqueous, is going to result in what? Okay, we do know that these compounds are dissociated into ions in solution. So when these two solutions are mixed and all these ions get to interact, what happens when, like with silver and sulfate? Well, okay, we've got all sulfates are soluble with the insoluble exception involving silver cations. So silver sulfate is insoluble in aqueous solution. So silver sulfate is going to precipitate out of the solution. So you have Ag plus and SO4 2 minus. So that's Ag2 SO4, but not aqueous. This is solid. Okay, now what about when the sodium and the nitrate interact? So all nitrates are soluble, no exceptions. Okay, so we just write then NaNO3, but we just put aqueous. Even though this does disassociate into ions in the water, because this is the molecular equation, we just leave this with its full chemical formula. All right, but now we're not done with the molecular equation because we need to balance this. So we've got two silvers on the right. Now we have two silvers on the left. We've got two nitrates on the left. Now we have two nitrates on the right. Two sodiums on the right, two sodiums on the left. One SO4 on the left, one SO4 on the right. So that's balanced. There's the molecular equation. Now, to write the ionic equation, we just break up any aqueous compounds into ions. In general, you only break up into ions aqueous compounds that are strong electrolytes. So you could have an aqueous compound that's a weak electrolyte, but then in that case, in the ionic equation, you wouldn't break it up into ions. However, with precipitation reactions, since we're only dealing with ionic compounds, well, all ionic compounds are strong electrolytes. If they're soluble, then they're strong electrolytes. So with precipitation reactions, the ones we're studying in this chapter, for the ionic equation, it's just, okay, if it's aqueous, break it up into ions. If it's not aqueous, then don't. So, okay, we've got two Ag pluses, aqueous, right? It is aqueous. I mean, that's the idea. The ionic equation is going to be more descriptive of the physical reality. You've really got these aqueous ions floating around everywhere. It's not these aqueous AgNO3 units. It's these aqueous ions, right? Plus 2NO3 minus aqueous, right? This is more descriptive of the physical reality. Plus, then you've got Na plus aqueous plus SO4 2 minus aqueous. Then you've got, you don't break this up, right? Solid. Then 2 Na plus aqueous plus 2 NO3 minus aqueous. So there's the ionic equation. Now, the net ionic equation, we just cancel any spectator ions in the ionic equation. So these 2 NO3 minuses are spectator. This is 2 Na plus, the subscript 2 here. And these are spectators, so we're left with the net ionic equation. And there we go. Okay. Part B, let's write the molecular equation. So barium chloride aqueous plus zinc sulfate aqueous. So now when these ions all get to intermix and interact, what happens when the barium and the sulfate ions interact? So sulfates are all soluble with the exception of so one exception involves barium. So, okay, this is BaCl2. Okay, so barium, Ba2 plus and SO4 2. This is the resulting compound. This is solid. And now when the zinc and the chloride interact, so chlorides are soluble and zinc is not one of the exceptions. So let's see. Now you've got zinc 2 plus and Cl minus. So ZnCl2 aqueous. Okay, now, but we're not done with the molecular equation. We need to balance this. So 2 chlorines on the left, 2 on the right. 1 zinc on the left, 1 zinc on the right. SO4 on the left and SO4 on the right. A Ba on the left, a Be on the right. So that's balanced. Okay, now the ionic equation, let's just break this up into ions. So, okay, now 2Cl minus plus Zn2 plus SO4 2 minus. Okay, then we've got BaSO4 solid plus then Zn2 plus then 2Cl minus. Okay, there's the ionic equation. Now let's cancel the spectator ions, and we're left with the net ionic equation. There we go. Okay. Part C, where we're starting off with ammonium carbonate, aqueous, plus calcium chloride, aqueous. Now when these ions interact, you've got the ammonium and the chloride ions interacting, and ammonium ionic compounds that contain the ammonium cation are all soluble. So you have NH4 plus and Cl minus, so NH4Cl aqueous, and then the calciums and the carbonates interact. So carbonates are all insoluble unless you have a cation that's an alkali metal and the ammonium. But calcium is an alkaline earth. Yeah, so insoluble. So CO3 2 minus and Ca2 plus. So CaCO3 solid. Now let's balance this. So one calcium on the left, one calcium on the right. Two chlorines on the left, now two on the right. Two ammoniums on the left, two on the right. And a carbonate on the left, a carbonate on the right. So that's balanced. Now let's write the ionic equation. Let's break this up. So you have two, the subscript 2, NH4 pluses, aqueous. Then a CO3 2 minus aqueous. A Ca2 plus. 2 Cl minus aqueuses. Okay, then you've got a calcium carbonate solid and 2 NH4 plus and 2 Cl minus. Okay, there's the ionic equation. Now let's cancel the spectator ions, and we're left with the net ionic equation. Okay. Okay, same type of problems. Let's write for part A, we've got sodium sulfide aqueous plus zinc chloride aqueous. Now, when these ions interact, you've got sodium chloride. Well, that's going to be aqueous. We know that. Then zinc sulfide. So sulfides are insoluble with the exception of alkali metal, compounds containing alkali metal cations and the ammonium ion. Well, zinc isn't an alkali metal. Zinc's a transition metal or a post-transition metal. So you have Zn2 plus and S2 minus. So that's zinc, just one zinc, one sulfur, solid. Now let's balance this. You have one sulfur on the left, one on the right. Two sodiums on the left, now two on the right. Two chlorines on the left, two on the right. A zinc on the left, zinc on the right. So there we go. Now, so the ionic equation, you have 2 Na plus aqueous and S2 minus aqueous, a Zn2 plus aqueous 2Cl minus aqueous 2Na plus aqueous 2Cl minus aqueous, and then there we go. Now the spectator ions, we cancel, and we're left with the net ionic equation. So zinc 2 plus aqueous plus S2 minus aqueous, then zinc sulfide, solid. Okay, part B. You have potassium phosphate aqueous. And then strontium nitrate, and they're giving us a coefficient here. Aqueous. Okay, now when the potassiums interact with the nitrates, all ionic compounds containing potassium cations are soluble. So K plus and NO3 minus, you'll get KNO3 aqueous. And then when you have strontium cations interacting with phosphate anions, strontium is an alkaline earth metal, Sr2 plus. And so we've got, let's see, all phosphates are insoluble with exceptions involving alkali metal ions and ammonium ions. So that's not, doesn't include strontium. So you've got an insoluble strontium phosphate, Sr2 plus and PO42 minus. So SrPO4 solid. Or no, phosphate is PO43 minus, so it would be SR3 PO42 solid. Okay. So yeah, I think they were just trying to help us with the balance here. That's why they're including this coefficient. So we've got 3 strontiums on the left, 3 on the right. Then you've got 6 nitrates on the left. So we need a 6 here. Then we would need a 2 here to balance the potassiums. So that should be balanced. Let's see. So if A is equal to PO4 and B is equal to NO3, then we've got K3A plus SRB2, then KB plus SR3A2, is that right? K3A, SRB2, KB. Yeah, okay, so now the A's are balanced. Now the K's are balanced. Now the SR's are balanced. And the B's are also balanced. 6 on the left, 6 on the right. So there we go. There's the molecular equation. Now, the ionic equation, we've got 2K plus aqueous, 2PO4 3 minus aqueous, and then you've got 3SR2 plus aqueous, then 6 NO3 minus aqueous. Or no, this was 6 here. And then 2, yeah, now 6K plus aqueous plus 6 NO3 minus aqueous, and then SR3 PO42 solid. There's the ionic equation. Now let's cancel the spectator ions, and we're left with 3SR2 plus aqueous plus 2 PO4 3 minus aqueous, and there we go. There's the net ionic equation. Okay, part C, you've got magnesium nitrate, aqueous, sodium hydroxide, aqueous. And so when the magnesium interacts with the hydroxide, magnesium is an alkaline earth metal. Okay, hydroxides are insoluble, but an alkaline earth metal is not an exception except for barium. But barium is not magnesium. So magnesium Mg2 plus, so an OH minus, so this is going to be solid. And then the sodium nitrate, that's going to be soluble. All sodium ionic compounds are soluble. So NaNO3. aqueous. Now we need to balance this. Magnesium on the left, magnesium on the right. Put a 2 here to balance the nitrates. Sodiums are balanced. The hydroxides are balanced. So there's the molecular equation. Now the ionic equation. Then 2NO3, 2 Na pluses. Okay, now an Mg. Or no. We do. So this doesn't break up. And 2. Okay, there's the ionic equation. Now let's cancel the spectator ions, and we're left with the net ionic equation. Okay. Which of the following processes will likely result in a precipitation reaction? If you mix a sodium nitrate solution with a copper 2 sulfate solution, or you mix a barium chloride solution with a potassium sulfate solution. So, okay, we'll have sodium and sulfate interacting in this first solution. So, no ionic compound with a sodium cation is going to precipitate out. All right, now copper 2 and nitrate. So nitrates are all soluble. All nitrate ionic compounds are soluble. So we're dealing with sodium cations and nitrate anions. Nothing's going to precipitate out. All right, so now what about B? So barium, Ba2 plus, and sulfate. So sulfates are soluble, but an insoluble exception is involving barium. So there we go. We can say that part B is going to be the most likely to result in a precipitation reaction. So we've got this barium chloride is telling us that this is a solution. So this is aqueous solution, right? And potassium sulfate and so we know the Ba2 plus and the SO4 2 minus, when they interact, that's going to form a precipitate. Now, what about the potassium and the chloride when they interact? Well, anything involving potassium is going to be soluble, any ionic compound involving potassium. So K plus and Cl minus, just KCl, aqueous. There's the unbalanced molecular equations. Now to balance this, now the potassiums are balanced, the chlorines are balanced, the bariums are balanced, and the sulfates are balanced. So now let's write the ionic equation. So Ba2 plus, and then 2 Cl minuses, then we have 2 K pluses, and an SO4 2 minus. Okay, now this stays solid, and then you've got 2 K pluses and 2 Cl minuses. Okay, now let's cancel the spectator ions, and we're left with the net ionic equation. There we go.